So, hello everybody, I'm Camille Jestin. I'm working as a geophysicist for Phebus Optics. And today I'm going to present my work on the relationship between distributed acoustic sensing data quality and gauge length value. So, just to be brief, I'm going to introduce how DAS system works. So a laser pulse is sent along the fiber, and at each point of the fiber, because of asperities intrinsically present in this fiber, a part of the light is backscattered to the DAS system. And this backscattered light contains the information on the strain in time and space along the fiber path. So when an acoustic event occurs along the fiber is stretched with compaction and extension of the cable. And the backscattered signal is phase shifted. And the phase shift is proportional to the strain. And this is what we can see in this formula, with epsilon the strain and delta phi the phase shift. So more commonly, the DAS data are expressed in strain rate, which is the derivative in time of the strain. And the DAS measurement involves measuring the difference in the phase of the backscattered light between two positions, so here A and B, and the distance between the 2 points is named the gauge length, and it appears here as GL in the formula. So, So the response of the gauge length is that of a moving average filter applied along the fiber, and this results in notches at a wave number of n on GL, and the first notch appears at 1 on GL here. And we are going to study the effects of the gauge length on data quality due to those notches. And to study that, we focus on a seismic campaign led in November 2019 in Svelvik, which is in the southwest of Oslo in Norway. And this survey has been conducted in the small-scale CO2 field laboratory, part of the project CO2 Field Lab, coordinated by the CTEMPs, which is a Norwegian company, since October 2019. It's an Excel infrastructure, which is open for national and international R&D activities. So this site consists in tests in the conversion of an existing well, here number 2, to an injection well, both of CO2 and water. And around this well, we have 4 monitoring wells, so M1, M2, M3, and M4. Which have been drilled at around 100 meters depth, and they cover a diamond around the injection well. So in those monitoring wells, we have different fiber cables installed. So these cables have been built by Solifos, and for this acquisition, I'm going to present now, we achieved the measurements along a standard monomode fiber using a Phebus A1R developed by Phebus Optics. So this campaign consists in a well-to-well seismic with a P-wave sparker installed in M1 well. So here we can see the first results computed with a gauge length of 2.4 meters. So this is the strain rate, so expressed in nanometer per meter per second, obtained after 28 stacks. So we can see the signal we have in the 4 different wells, so M2, M3, M1, where the source is located, and M4. And we see that the first arrival forms like 2 peaks due to let's say the back and forth, to say that, the way back and forth in the well. And we have a symmetry between M3 and M4 due to the geometry of the acquisition. So that's why for the following of the study, I'm just going to focus on M2, M3, and M1 wells. So during this campaign, we varied the source depths between 57 and 67 meters depth with 1 meter step. So here are presented several results at 57, 61, 63, and 67 meters. We see that the first arrival time is still the same, but we have the distance between the two peaks, which is reducing when we increase the source depth. So for the following of the study, we focus on the 67 meters source depth. And we are going to study the effects of the gauge length value on the DAS data quality. So using the Phoebus A1R DAS system, it's possible to vary the gauge length value in post-acquisition processings. And then for the same data set, we can compare the results and the data quality for various gauge lengths. So here, as I said before, we focus on the 67 meters source depth. And we can see here the first arrival, but also some reflections in the signal. And we vary the gauge length between 2.4 and 8 meters, and we have a fixed corner frequency at 1 kilohertz. So here are the results obtained with the 4 different gauge lengths, so 2.4, 4 meters, 6.4 meters, and 8 meters. And we already can see that we have a kind of a smoothing of the strain rate, so still expressed in nanometer per meter per second here. So we have a smoothing of the background noise, but also of the signal of interest, so of the first arrival here. If we compute the signal amplitude and the signal to noise ratio, so we can compute it considering the window between the two red lines here. We can see that the strain rate, the signal to noise ratio values are similar between the different gauge lengths, meaning that the smoothing, as we saw before, operates both on the signal and on the noise part of the strain rate. But we observe a clear increase of the signal amplitude when we decrease the gauge length value. We then lose a big part of the information when the gauge length is too high, and we even observe a plateau when the gauge length is higher than 6.4 meters. So now if we look at the F lambda space, we clearly observe the influence of increasing the gauge length value. And we see the narrowing in the signal zone, not only in the wavelength direction, but also in frequency. So this is something we have to consider to avoid any aliasing effects in both directions. So we saw here that the gauge length of 2.4 meters looks like the best adapted for this seismic campaign. But we can wonder if this gauge length of 2.4 meters is like a standard value we can use for every campaign. So for that, I'm gonna focus on another case of study, which is a seismic campaign, a vertical seismic profile campaign led in July 2020 in the southwest of France. And the source used here was an air gun located at around 100 meters away the wellhead. And this well is also equipped with standard fiber, so standard monomode fiber. And the well is a vertical well, which is around 2 kilometers deep. So to study the influence of the gauge lengths and data quality, we consider 3 different gauge lengths, so 10 meters, 30 meters, and 50 meters. And we already can see that at 10 meters, we have background noise, which is much higher than for 30 and 50 meters. And what we can see also is that all the gauge length values used here are higher than previously. So we decide to focus on the first arrival again, so still between the 2 red lines, and we compute the signal amplitude. So at the contrary as before, we can see that for the whole used gauge length, we have a similar signal amplitude. But we notice that the signal to noise ratio is much higher when we increase the gauge length value. We even observe a plateau at 30 meters gauge length, meaning that we reach like the best value we can have for this campaign. We then see that for this case of study, short gauge lengths are not adapted at all for good observation of the signal of interest. So as a conclusion, it's a bit short. The gauge length value appears as one of the most important parameters in DAS acquisition campaign, and this parameter needs to be adapted with each context of survey and related expected wavelengths. The ability to vary the gauge length value after acquisition appears as a good opportunity, at least for a first campaign, to adjust it to obtain the best data quality associated with the context. So, thank you very much. And if you have any question, it will be a pleasure for me to answer.
Thank you, Camille. That was great. All right, let's see. Do we have any questions in the chat box?
It looks like we do have one here from Patrick. Sorry, it's a bit of a long one.
Reading it.
As you mentioned, it would be great to have a low enough gauge length, but shouldn't this value be chosen based on the expected apparent wavelengths along the fiber?
Yeah, of course.
It would be great to have the plots that you showed with gauge length as a fraction. Yeah, go ahead, sorry.
Yeah, that's exactly the interest of varying the gauge lengths. If you if you expect like low wavelength value, you will decrease the gauge length value, and for higher wavelengths, you would expect higher gauge lengths.
All right, any other questions out there? All right, so then we'll go on to our next speaker. Next speaker is Jonathan Ajo-Franklin. He's a professor in the Earth, Environmental, and Planetary Sciences Department at Rice University. And the title of his talk is Avoid DAS-aster, Issues to Consider Before Your Next DAS Experiment. Great title.
Hello, everybody. Thanks for giving me the opportunity to say hi and to present a little bit of our recent mistakes, I should say. This is just going to be, it's not a super structured talk, right? Because it's all about mistakes, which don't have quite the same order as a scientific hypothesis. But a lot of the mistakes, I was joined by many great students and postdocs who I've worked with in the field over the last probably about 6 years on DAS. So just to call out a couple, this is not to call out mistakes, but to call out people who helped me make mistakes. In particular, Feng Chang, Michelle Robertson, Shando, Veronica Rodriguez-Tabaladas, Avinash Nayak, and Nate Lindsay, who are all out in the field at various times as part of these projects, and most of whom are probably on the call too. Okay, so some things we've learned since 2014. So I'll start by saying this isn't a science talk. There are no new results. It's just kind of a triage of some challenges and complications, and I've tried to impose a little bit of order on them. There's probably a whole nother talk about processing mistakes, but it's not for this 12-minute interval. So, you make mistakes by, you screw up, and hopefully others can learn from them. So this is a talk which is mostly focused on dark fiber installations, because that's what we've been working on for the last couple of years, but many of the same issues exist to varying degrees for fit-for-purpose fiber networks, which we've seen a lot of great slides on. And so I kind of broke this down into 4 different topics. We've had a lot of problems with the time in the past, so you got to know when you are, when you're doing DAS acquisition. Array geometry is a big issue in DAS, which isn't usually there for conventional seismology. You got to know where you are. These issues of coupling and fiber installation, which a lot of folks have alluded to, you got to know what you're looking at, because sometimes with DAS data, it's not obvious what you're measuring, especially if you don't know that much about the network. I also talk a little bit about physical safety for systems, because that's something we've had some exciting experiences with. And last of all, you have to know how to manage your data, because the volumes generated by long-term deployments in particular, especially if they're remote site locations, are quite daunting. So I haven't solved that problem, but at least I can tell you that it's something you should think about. So first of all, knowing when you are, so keeping track of time. So obviously in seismology, the standard is to use GPS. And this is particularly important if you're interested in earthquake arrivals or active sources which don't have direct synchronization to your interrogator, or in situations where you're trying to coordinate with external networks to sort of build some sort of joint data product. The problem is, though, to get GPS time, you need sky, or at least a window or some access to it. And a lot of DAS deployments, especially dark fiber, happen inside of big buildings where it's difficult to get outside access. So this has been a problem we've dealt with in a couple cases. And when you don't have it, you're stuck with the internal clocks on DAS, which often have a large degree of drift, often on seconds per day kind of level. So here's two kind of examples where, to varying degrees, we made mistakes. The first one is the West Sacramento experiment, the FOSSA experiment. And there's Nate. I'm not blaming Nate, but this is two examples where GPS was really tough to manage. So in this particular case, we're installing an IU in the middle of a giant point of presence, which didn't have a lot of access to external walls or feed-throughs. So we were not able to use an external clock in this particular case. And the second example is down at the Collab test bed in the SURF, the Sanford Underground Research Facility. So in that case, we're almost a mile underground. So there's definitely no GPS antenna for us in that case. So, you know, like, I'm just going to talk a little bit about problems and solutions. So what's the impact of bad timing on a DAS experiment? So without your GPS or some sort of accurate pulse per second kind of synchronization, these systems fall back on the internal clock or NTP, and an internal clock can slip seconds per day. So in the case of FOSSA, you know, when we started out on it, we actually weren't too worried about time because we're mostly interested in ambient noise with short correlations. But by the end, we were really interested in earthquake seismology. And so it ended up that after some laborious analysis, Avinash Nayak went ahead and computed through cross correlation with an external reference how much we slipped over that time period with that, you know, just the quartz clock inside the instrument. And it ended up being an irregular rate, but between 1 and 46 seconds over the course of the experiment. And that's, you know, over 7 months. So it's really an important thing to kind of have a strategy for acquiring accurate time. And this is known to all seismologists, but, it's particularly significant in these two examples. So some solutions which helped. For the mine case at SURF, we ended up synchronizing the DAS to a rubidium atomic clock. And so the clock is synchronized on the surface and can hold time to within kind of microsecond, sub-microsecond drift range, and then synchronize the clock on the DAS using a PPS pulse. So, so that was one great solution, as long as you're willing to go ahead and babysit one of these highly accurate clocks. Important to talk to your IU vendor to make sure you can actually do the synchronization if you're interested, but it was one solution. You also need to make sure that your clock is kept in good shape in the sense that they lose their synchronization if they lose power. So especially in places where there's irregular power sources, you need to have a UPS. For the next point of presence deployment, this is our current dark fiber experiment in the Imperial Valley. We ended up finding a way to route a cable outside, but it's really important to start with that as an assumption which you need at the very beginning of a project, rather than having to bootstrap it and bring along a sawzall and cut a hole in the side of somebody's building. There are more exotic solutions because obviously people who do things like seafloor seismology have dealt with this issue of clock accuracy, and they're possible, but you want to decrease your need for them. So plan for time standards. A second kind of thing is you got to know where you are. And so this comes down to this question of defining the geometry of your array. If you're using an inertial sensor, which a lot of folks are familiar with, you lay out your sensor, you take a GPS location of it, and that's it. But for dark fiber, particularly on pre-installed networks, we only have really weak constraints on fiber location, plus lots of slack, because these were installed for telecom purposes. So just as an example, vendor KML files, which show the geometry of a network, can be off by tens to hundreds of meters. In this particular case, we actually have 3 versions of the KML file, and they're all pointing the fiber in different locations. So this is just a map of where the fiber was supposed to lead from the ILA and where it was actually located at. So tap testing of these GPS locations is often the best way to determine location, and you really need to plan time for a reasonable number of locations to define that geometry, or use that really cool trick with the GPS located car, which we saw a little bit earlier in this workshop, but I haven't tried that yet. So another thing to remember is just not to change settings. A lot of the IUs are now very smart and they attempt to optimize things. But if you change settings before and after tap tests, you often end up in situations where they move slightly, between acquisition runs. So that's something to kind of think about, or at least to test the next time you try it. It all varies between IUs. This is just an example of a tap test at this particular location. You're picking the apex, where the surface location of the fiber is from bollards, and that's Todd Wood and Michelle Robertson doing the hard work. Something to mention is for short arrays, maybe this doesn't seem like a big deal, but if you've you've got 28 kilometers of array and it goes over other people's property, which you need to get landowner access for, it can become a very big deal. So just think about where you are. If you don't have enough taps, sometimes you can infill with natural noise sources, which happen along the fiber and which are really easy to pick out. And so this is a fiber map, which actually was just from yesterday. Feng Chung is working on it for our Imperial Valley array, just showing where we have tap tests in the north and a bunch of other locations, which we think are natural noise sources, anthropogenic natural noise sources, which we're trying to use to kind of align things. But you should really be forewarned that there are many anthropogenic noise sources, and you don't exactly know where they're emanating from. So particularly in urban areas, it may be hard to ID exactly where the source is happening, and therefore you're not going to get plus minus 10 meter or even 50 meter accuracy in some cases. So just go into that clear-eyed that you're not, going to locate it out to, a centimeter or whatever you think your GPS is accurate to. This is an example of a noise source from a vibrating highway overpass, which is super energetic. You can see it for 5 kilometers, but it's super hard also to figure out exactly where that vibration is being pumped into the ground and what to call your location. So just be forewarned. For fit for purpose networks, it's a little bit easier. You know where the fiber is going in, you put it there yourself. One of the challenges though is that often fit for purpose arrays, particularly if you're aggressive on geometry, can have a lot of corners and short sections, which can be hard to ID. So I mean, typical gauge lengths, we've seen some nice boxes with 2 meter gauge length, but usually we're operating in systems with on the order of 10 meter. So that means that gauge length is spread across corners and around things, and it can be actually very hard to actually pick apexes in that environment. So you consider tap testing on both turnarounds and on long straight sections to help mitigate this, issue and help you get a better geometry for your network. Also, keep track of your splices. Splices can be a huge deal. And remember that the tap test is only as good as your survey method. So if your GPS is accurate to 10 meters, your network's going to be at least that bad, if not more. So geometry assignment has actually been a little bit of a rite of passage. I think at least 4 different students and postdocs have assigned geometry to this particular network, and they've all been slightly different, especially for different fiber systems. So now I'm just going to go on to, you need to know what you're looking at too. And this is this issue of coupling and installation. So when you're exploiting fit for purpose arrays, you know exactly how the fiber is coupled to soil or rock. But when you're using these pre-existing networks, especially dark fiber, it's best to know the installation practice and details of where it was installed. I almost put down a contract for renting some dark fiber, which actually in the end, it turns out was almost entirely on poles. So you don't want that situation if you're doing seismology. One of the big issues we found is attached fiber on utility poles or bridges and overhead rail. So even if they're parts which are trenched or installed in conduit, often you'll have sections which run on rail lines, for this example, and down here it goes across a bridge, again on a tubular, but this is a long, long bridge, and there's sections of this array which are on similar encapsulations. And so when you're in these uncoupled zones, I think Nate and Eileen showed an example of an earthquake on this earlier on. You really are not getting great data. You're mainly looking at the resonance of the infrastructure and airwaves which are traveling through the conduit. So just be aware and attempt to determine the surface-subsurface geometry beforehand if possible. And the best thing is to get engineering drawings for the fiber provider. Even when fiber is known to be subsurface, coupling can still be an issue. And this is not as commonly a problem with us. We've been happy with a lot of our deployments, but the worst case from our limited experience are scenarios when the fiber is in kind of layers and layers of conduit. So like look down here where you've got the fiber cable, which is loose packed in a bundle, and then is loose packed in another conduit, and then is in another conduit, and then is buried. So in situations like this, you can really degrade signal quality, especially at the higher frequencies. So again, it's always useful to have these engineering drawings beforehand. If you know anyone involved in the fiber installation, this happens once in a while. They typically know all the skeletons or where all the skeletons are buried and like what actually happened when something went in the ground. And we had that case in one experiment. The next thing is you got to know what you're looking at from the perspective of physical system safety. Now, this is the most dramatic slide in this. So we had an interrogator unit deployment in Alaska as part of a project. Someone broke into the container and set it on fire and destroyed all of our interrogator units. The DAS luckily wasn't in there, so this is a DTS and a distributed strain system, which ended up being torched. In retrospect, it would have been nice to have a thicker door, taller fencing around the site, more monitoring. We did record the arson on a game camera, so that person, there's still a warrant out for his arrest in Fairbanks. But the moral of the story is site security really matters, and if you lose your interrogator unit and all the important equipment, it's not going to matter if the data would have been wonderful off your network. So, physical system safety is something to think about. And finally, we have to think about how do you manage data, which is really an endless struggle with DAS. And as I said here, I don't really have any big solutions, but it's something you should think about beforehand. I mean, assuming you're generating this beautiful data, what do you plan to do with it? You need a strategy for transferring it from wherever you're acquiring data to your home institution, for storing it short term while you're doing processing, and for archiving it, because it's got to be a cradle to grave kind of perspective on these data volumes. So you remember with the ballpark, for a large dark fiber network, you could, if you were sampling at high rates, 20 terabytes a week, and you multiply that over long-term deployments over years, and you got to move that data from your IU to your home institution, which your IU might be in some remote location. So we've often done it via SneakerNet, where people took boxes of external hard drives, things like that, and actually physically carried them, and we uploaded them to our cluster. And this is the system which we used up until recently, which was kind of a RAID array, which was hooked to a storage server, which is about 1.2 pets now, which is connected to a larger cluster, which we use for processing. Because you need to get the data to where the processing is happening, and that's critical. Now with our remote field systems, we've kind of switched over another design, so we don't have to serve them as frequently, where we have local RAID systems, and then we maybe have lower speed links to do data QC. But this is not really a good solution. Our solution is not sustainable, so we need a path to get to smaller storage footprints, or perhaps products and compression. So this is just kind of 3 possibilities, and you've seen this slide maybe from other talks I've given. Option 1 is to store everything, and if we have a growing number of IUs in the community, and a growing number of people recording continuously, each IU is maybe 0.4 pets per year, up to 3 if you are going fast. And so just to give you a sense, that's, could be 50 8-terabyte hard drives or a 60 kg storage server every year, and that has to come off your grant. So, you need some way of maintaining that. Another option is compression, and at first I was actually pretty pessimistic about this option really making a difference, but there's been some recent stuff which makes me feel it may be more of an option. And the last is product. Start being more selective about what's actually stored, or how things are downsampled, and considering special purpose data products which are customized to narrow application intents, where you can cut storage down pretty dramatically. But the moral of the story is not to choose any of these decisions in particular, but to be clear-eyed at the beginning of your project about the amount of data you're going to acquire, what storage will cost, and what will happen to it all at the end. So that's a couple lessons learned. There are lots more, but that has to be over some beer at an actual real AGU rather than at the workshop. But you should know when you are, have this plan for timing, know where you are, how you're going to define your network, know what you're looking at, gather as much information on the network as possible, and think about physical safety. And last is how to manage your data and what's gonna happen. I know that we're all aggressive about data management plans, about all these magical things which are going to happen to our hundreds of terabytes of data, but it's really hard to do this affordably, especially when your grant runs out, and then who's going to pay for all the storage afterwards. So think about this data management, processing and archive problem too. And that's it. Thanks for listening to all this rambling. It's not a single story, but lots of little stories in between. And of course, it's been funded by Department of Energy and Department of Defense.
Awesome.
Happy
Thanks,
to take
Jonathan.
questions.
Thanks, Jonathan. That was great. I think we have time for a question or two.
We've got one quick one here. How about using internet to sync the clock?
Yes, you can do that. So network time protocol is typically good within around a second. And as long as the interrogator unit, sorry, I see here IU equals interrogator unit. Yes, sorry about that. And so if you're happy with the second time synchronization, and the vendor actually has NTP corrections built into their acquisition system, that's an option. There's also something called precise time protocol, which can be used to get microsecond accuracy, but most systems are currently not set up to handle that. And I'm happy, there's lots of vendors who are on this workshop, so they can, if they've got ideas on how to do this. There are some cases where you don't necessarily have that much good network access, and that's like one of our current projects. But in other situations, if you're in a point of presence for the internet, you can certainly get enough network access to do PTP pretty well. So it's kind of on the technique side, but something worth thinking about.
All right, great. So we're going to move on to the next talk. The next speaker is Adam Booth. He's a lecturer in exploration geophysics in the School of Earth and Environment at the University of Leeds. And he couldn't join us live today, so it's going to be a recorded presentation. And he assured me that if you had any questions, you could email him And so I'll shoot the email into the chat right now. All right, someone let me know if you guys can hear it.
Hi, my name's Dr. Adam Booth, and I'm Associate Professor of Applied Geophysics in the School of Earth and Environment at the University of Leeds in the UK. First of all, thanks very much to the organisers for inviting this talk and also for allowing it to be presented in a pre-recorded format. Sorry that I can't be there to present and discuss it live, but it is 2 AM in the UK, and I assure you that I am asleep. But I'm dreaming of distributed acoustic sensing, and particularly an experiment that we were able to do in summer 2019, the first of its kind, where a length of fiber optic cable was installed in a borehole, and we were able to do some distributed acoustic sensing there. It was a really interesting data set, loads of really cool insights about the seismic structure of this particular glacier. But with the benefit of hindsight, maybe there's more that we could have done to enable
Looks like my internet has cut out. Let me try this again. Bear with me, everybody.
It's okay, Rachel.
Hi, my name is Dr. Adam Booth, and I'm Associate Professor of Applied Geophysics in ice. What I'll do in this talk is give you a quick crash course in the seismic structure of glaciers, why we're interested in it. I'll show you some of the data and then show you some of the limitations of our experiment. So what you're looking at here is a map of Greenland. The orange square shows our study glacier. It's called Store Glacier. It's a major outlet of the Greenland ice sheet.
I don't think it's showing the video on the screen.
Got it. Thank you. All right.
500 meters per year and discharges icebergs into Baffin Bay. Now, if we're going to predict how this glacier might evolve in a warming climate, this is where seismic measurement comes in. Seismic properties sense the mechanical properties of the ice, which can be really important to feed into dynamic ice flow models. So what do those seismic properties look like? Here's a schematic cross-section through a glacier. You've got some thickness of ice, in our case it's around 1 kilometre, overlying some deformable sediment layers and eventually underlying bedrock. We're interested in the ice and the sediment layers. The sediment layers dynamically evolve in terms of their hydrology, and the interaction of the ice and that hydrological system is a real big control on ice movement. What we normally expect for ice itself, though, is that for the majority of the glacier, it will be isotropic, P-wave velocity of something like 3,750 meters per second. At some point, we might have a flow fabric that develops, so all of the ice flow causes all of the ice crystals to align, and the fast axis of an ice crystal gets orientated vertically. So at this point, a vertical P-wave might be propagating at over 4,000 meters per second. Go deeper into the glacier, and eventually you'll get into what we call temperate or warm ice. It's where the ice is at its pressure melting point. So there is intracrystalline water, liquid water, between the crystals of ice there. So we might expect P-wave velocities to reduce. We'll come along with a seismic reflection survey. We measure reflected travel times, we can build a velocity model, we can measure the reflection coefficient at the base of the ice and say something meaningful about the sediment properties, and we can also measure the attenuation rate of the seismic energy. This has been shown to relate to ice temperature and is an important thing to bear in mind when it comes to thinking about the mechanical deformation of the ice. Now, other experiments I've done around Greenland suggest that Q in ice in this area is something like 300. So we were able to do a DAS experiment on Store Glacier to see if the the borehole insight would allow us any better constraint of all of these different seismic properties. So here's a quick view of operations on Store Glacier. What you can see in the main picture is our drilling equipment. We drill a vertical borehole using hot water methods. So water is pumped from nearby meltwater streams into a heating and pressurizing system. The water is pumped through the hose over the top of the drill tower, and that pressurizing hot water is used to melt and blast a vertical borehole, probably on the order of 10 centimeters across. When we reach the glacier bed at 1,043 meters, we then install fiber optic cable. Initially, that borehole is full of liquid water, but then over the course of the next day, that water freezes and the cable becomes very, very well coupled to the surrounding ice. We then measure distributed acoustic sensing using a Seismology DAS system with a 10-meter gauge length, and the seismic energy that we're recording is basically me hitting the surface of the glacier with a 14-pound sledgehammer. We have various shot locations around the borehole. Each of them is something like the sum of 35 individual shots. Here's the distribution of all our shot locations around the borehole. You've got the borehole there in orange. We did lots of zero offset shots just here, but then there's also a lot of walk around and walk away shots to something like an offset of 500 meters from the borehole. Now I'm only going to show you the zero offset shot in this particular presentation, but there's a paper out there in Geophysical Research Letters. If you type those search terms into your search engine of choice, then you will find the paper and you can see some insight from some of the offset shots as well. So here is an example of a zero offset VSP record. It's pretty nice, really pretty clean. Our hammer shots go down the full length of the cable, and also in some other shots you can see you get reflections coming back up. So we were really pleased with the general data quality, the detectability of the seismic energy. It's all looked very promising. What I did here was to show some frequency content in the data, which I'll come back to in just a second, but I'll first just do the diagnostic anatomy of this VSP. What I think we've got is the direct P wave there marked in red. There is also some scattered P waves arriving, which I think are coming in from nearby crevasses. If you get your eye in closely, you can maybe see that there's a tube wave coming down. But what I did was a basic exercise with a 50-meter gap to derive this model of vertical P wave velocity. When we put that in the context of the glacier, then for the majority of the ice thickness, it looks that the seismic energy is traveling at 3,750 meters per second. But then something like 900 meters, there's a step up to faster velocities, which may well coincide with the location of this developed ice fabric. And certainly that's really consistent with observations from surface seismic data in a similar area. We also noticed that in the very bottom of the glacier, the velocities are slower, and maybe that's indicative of temperate ice, this warm ice where we've got liquid water within the crystal, between ice crystals. However, let's take a look at those frequencies again. The three spectra that I've plotted correspond to depths of 50, 500 and 800 meters, and the dominant frequency in the seismic data is always around 200 hertz. So it's a nice high frequency source. And I thought that we'd be able to measure quality factor, get some indication from on glacial temperatures from spectral ratios of these arrivals. But the frequency content really doesn't change very much, and that's a little bit surprising. What I was able to do at least was to look at the amplitude of the seismic energy. So this was after correction for geometrical spreading. So all we've got is kind of the amplitude decay that can't be explained by geometric processes. And you can see there's a nice linear reduction in amplitude with depth, and then there's a big kink at around the 900 meter mark. And again, I think that this is related to the less efficient propagation through the warm ice. But it would be nice to be able to put some Q values on this, but I'm concerned by the lack of change in those spectra. So I'm curious about this frequency behavior. The first question is, should there even be a measurable frequency shift in these data? What I've done is enlarged the spectra just here, and you can see that, noise aside, all of these spectra share the same dominant frequency as around 200 Hertz. What I did was to take a Ricker wavelet and to propagate that Ricker wavelet through a representative ICE model. So it's got a dominant frequency of 200 Hertz. It propagates for 1,000 meters at 3,750 meters per second through ethereal with a Q of 300. Similar to what we should expect for ice. And I'm showing the spectra of those wavelets here. So in blue is the unattenuated wavelet, in green is the attenuated one. And you can see that indeed there should be some detectable frequency shift. The dominant frequency goes from 200 Hertz to 170 Hertz. So even though ice is an efficient propagator of seismic energy, for a Q of 300, we still should expect to see some frequency change. So what's going on? So what I think explains these observations is an interplay between the frequency and wavelength components in the seismic data and the gauge length in the interrogator. And this is a concept that I wish I'd known more about at the time of designing the survey, but I didn't. And as it happens, we either got really lucky or really unlucky, depending on which way you look at it, and I'll leave you to decide. But as I now know, the seismic response is derived using the average strain within a given gauge length of the cable. So if we take a seismic wavelet arriving at the cable, if it turns out that its wavelength is the same as the gauge length, because we're averaging, we'll cancel the peaks and the troughs and we'll end up with zero response. So in that sense, the DAS cable has some wavelength filtering characteristics. The practical implication of that then is that the gauge length should be less than 1/2 of your shortest expected wavelength component. And it also means that only wavelength components longer than 2 times the gauge length will be faithfully recorded. So how does that stack up for our particular survey? What we had was a system with a gauge length of 10 meters, which means that there's probably going to be some cancellation for any wavelength components shorter than 20 meters. So what we saw was wavelets with a 200 Hertz dominant frequency. They're propagating at 3,800 meters, and that means that the dominant wavelength is 19 meters. So we could probably expect that we are doing some damage to the high frequency components in our data. Maybe that's why our spectra look as consistent with depth as they are, and why our Q analysis is really rather limited. If anyone out there knows of any ways to try and reconstruct some of those amplitudes beyond simply a bit of scaling, then I'd be interested to find out. But I wouldn't be surprised if that means that those high frequency components are unrecoverable. So what went wrong? I think during the early stages of the acquisition design, a lot of the geophysicists involved in the discussion are more used to using other seismic sources on ice than a hammer and plate source. For example, the RV use a vibrator truck in Antarctica, the British Antarctic Survey use explosive seismic surveys, and the dominant frequencies you get from these are probably a bit more like your typical industrial seismic surveys. A hammer and plate source does radiate higher frequency energy, and therefore, with hindsight, an interrogator with a 3-meter gauge length could have been a better choice for us. Now, that said, it was still a great experiment. The velocity information that we got out were really useful. Elsewhere in the data, from the offset shots, we see both P and S arrivals. We see reflections from the glacier bed and some of the subglacial sediment. So I'm still really pleased with the data that we got. It's just maybe a little limited in the degree of Q analysis that we can do. So just to wrap up, I think we showed that there's enormous potential for DAS methods within glaciology. We got a large and very comprehensive data set that's still being analysed as we speak. And I think all round we did a very successful demonstration of the method. However, we also did a very good demonstration of what happens when you don't quite get your basic survey design right. And I just wish I'd been more heavily involved in the early stages of planning to sort of facilitate some of those discussions. Communication is definitely key. I'd just like to thank first all of the project team involved with this analysis. It's the Responder project, which is funded by the European Research Council, involving academics from the Scott Polar Research Institute, from Aberystwyth University, myself at Leeds, and of course, Silixa. A big thanks to them for providing the advice, the systems, and the personnel in the field. I'll also say thanks to you for watching this presentation, and if you've got any questions, comments or advice on how to reconstruct the high frequency content, then please do email me or you can tweet me as well. Hope to hear from you soon. Have a great workshop and stay well.
All right, thank you to Adam. And again, if you guys have any questions, please feel free to email him. All right, and then our next speaker, our last speaker in the user experiences is Julia Correa. She's a research scientist at Lawrence Berkeley National Laboratory, and the title of her talk is SOV-DAS for realizing the potential of permanent reservoir monitoring.
Thank you for this introduction. Just give me a second so I can pull up the presentation. Can you all see my screen now?
Yes.
Okay, yeah. Great. So, okay, thanks everyone. So I'll be talking about how to build an on-demand permanent seismic monitoring system by using DAS and permanent seismic sources called the surface orbital vibrators. So originally Barry Frightfield was going to give this presentation here, so I'm filling in for him. First, I just want to acknowledge all the collaborators. This is a long list of researchers and students and postdocs that keep working on the development of the DAS and SOV system, but specifically I'd like to acknowledge, again, Barry Frightfield, Jonathan Ajo-Franklin, Thomas Daly, Roman Pevsner, and Todd Wood, who have been really leading the development of the DAS-SOV system. So conventional permanent monitoring systems often include the use of thousands and thousands of geophone receivers and large fiber-sized sources. Usually you also need a large crew to deploy this equipment and to operate this equipment, which often makes this type of acquisitions quite expensive. And because they're quite expensive, usually they're not acquired very often, which gives usually quite sparse temporal resolution. To solve some of these issues related to conventional campaign-based systems, we're proposing the use of DAS and permanent sources called the SOVs. Both of these technologies, so both DAS and the SOVs, they can be deployed permanently. They can be operated autonomously, so they have an autonomous operation, and they require minimum human intervention. So with this, the use of DAS coupled with permanent sources can help build a true on-demand permanent monitoring array. So the surface orbital vibrators, or SOVs, seen here in the picture, they work by rotating these eccentric weights that generate a vertical and horizontal force. And we have an installation of a 3-component geophone nearby the source to record all the 3 components of the seismic signal from the SOV. And as you can see in the picture, they come with this adjustable weight, so you can select the maximum force that you're expecting with the SOVs. And you also, the SOVs have a couple of different sizes, which will indicate what's the maximum force that you get and the maximum frequency. So this SOV here seen in the picture, it can go up to 80 hertz, reaching a 10-ton force. Because we're talking about a rotary source, the force of the signal actually varies as frequency squared. So the higher the frequency of the rotation, the higher the force. So this ends up creating an unbalanced frequency spectrum, which we deal with by deconvolving the sweep instead of cross-correlating, which what you would usually do with a vibro-sized source. So we have tested this system in a couple of different sites in the world. Actually, now we have a few more installations than what you see here in the picture. But one of the sites is the ADM carbon capture storage site. The ADM is a company in the food processing industry, actually. And in Decatur, Illinois, they have an ethanol processing plant, which is fully coupled to a carbon capture storage facility. And we have installed a surface fiber optic cable there with an array of SOVs. So the surface fiber cable is laid in 2 lines, which you can see here in red. And we have a combination of single mode fibers and engineered fibers installed on the surface. Along with the fiber optic cable, we have also 5 different SOV locations. So we have 3 SOVs along this line and 2 SOVs along this other line. So the objective here is obviously monitor continuously the CO2 injection using the surface fiber and the SOVs. So we installed a helically wound fiber optic cable, which had wounding at 30 degrees along the axis. Given that we only have surface fibers in the installation, we don't have any boreholes there with fiber optics installed. Having the helically wound fiber here is an important feature that will improve the angular sensitivity of DAS, given that DAS is a one component measurement. And the cable that we installed, as I said, has a combination of single mode fibers and engineered fibers that can improve the sensitivity of the DAS. So one interesting aspect of the deployment of the fiber optic cable is that we used a horizontal directional drilling. When we see surface fibers installed, they are usually installed along a trench. Given that these areas mostly are farmland, there were some buildings around and some infrastructure, we used a horizontal directional drilling to deploy the fiber optic cable so we can cause the minimum disturbance to the ground. And we then coupled the fiber optic cable putting a grout inside the hole. So one of the challenges that we had was the strong presence of ground roll noise on the data, which was difficult to be removed using normal noise attenuation processes. The ground roll noise was especially affecting the data quality for the SOVs that were located close to the DAS line. And because the ground roll noise is generated by slow-moving surface waves, they arrive at a similar time as the SOV-generated P wave reflections that we were expecting from the target zone, which was the injection zone for the CO2, the Mount Simon sandstone. So this was quite challenging for us to recover these P reflections from the injection interval. The way that the fiber optic cable was installed was that we had the standard single mode fiber spliced into the engineered fiber. And this plot here shows an example of one sweep that was recorded along the entire length of the fiber optic cable. And you can see the sweep was recorded on the engineered fiber, but it wasn't recorded on the single mode fiber. And over here on the right, you can see the migrated image of the DAS SOV system after the seismic processing. So we can see that there's reflections along the interest area, which is around the Mount Simon area. Also note that we have issues with reflection continuity along the fiber optic cable, which probably can indicate poor coupling, as we were hearing also from Jonathan's presentation. We see the reflections here, but then suddenly the reflections, they disappear, which probably are caused by poor coupling. And then I generated this synthetic seismogram here from well logs to match the reflections from the DAS SOV data. And the synthetic seismogram and the migrated image from the DAS SOV generally match, especially around the stronger reflections. I just want to point out here that the target area is at almost 2 kilometers deep. So this is quite an encouraging, this is quite an encouraging result, given that the application of surface seismic with DAS it's quite difficult due to the angular sensitivity. So this is quite an encouraging result that we can see reflections coming from almost 2 kilometers deep. So the other example of DAS-SOV deployment I want to show is from the Otway project. The Otway project is a carbon capture storage site in Australia. And the current plan for the project is to use primarily DAS installed permanently in 5 wells for seismic acquisition, coupled with 9 SOVs installed on the surface. So to monitor the CO2, they are using primarily DAS and SOVs there. And the seismic acquisition system with DAS and SOVs is acquiring data automatically every day, and the data is being processed automatically every day as well. And the end goal here is to have the daily images of the CO2 plume migration. So in the Otway project, we installed a dual SOV system so that each SOV location, there were 2 motor sizes there. The smaller motor here was set to go up to 105 hertz, and the bigger motor was set to go up to 80 hertz. And we decided on this based on our previous field tests on site. We needed the higher frequencies provided by the smaller motor, since the large motors could only go up to 80 hertz. And another aspect that we implemented was the addition of a quadratic sweep design. Here you can see in this plot of the sweep in time frequency, and the blue is the small motor sweep, and in red you can see the large motor sweep. And as I said, the large motor was programmed to have a quadratic sweep, and this was done so it would sweep for longer on the lower frequencies, and with this improve the lower frequency response. Because we are talking about rotary sources, once the SOV starts rotating, it hasn't really gained enough momentum in the beginning of the sweep. So this generates an unbalanced frequency spectrum with weak energy on the lower frequencies as the force increases, because the force increases as frequency squared with these rotary sources. So with the quadratic sweep design on the large motor, we can work around this limitation. And here you can see another plot showing the time frequency response, but this time this plot was generated using the response directly from the geophone. And on the right here, you can see the VSP data from the DAS installed in the injection well, and all 9 SOV locations here. And note that the signal to noise ratio for most SOV locations vary between 40 to 100 dBs, which is a pretty good signal to noise ratio. So
Julia, just to let you know, just a couple more minutes. And
oh, okay, almost done.
Thanks.
So we've compared the improvement in the frequency spectrum of running a quadratic sweep design and linear sweep design, and we can see pretty clearly this improvement in the lower frequencies as well. So just to conclude, the SOVs, we have tested the DAS and the SOV system in oil and gas projects, geothermal and CO2 storage, and the SOVs can be quite a cost-effective seismic source, especially for continuous monitoring. And using the DAS in combination with the SOVs, we can have a pretty good and reliable alternative for permanent seismic monitoring. For some acquisition types, for example, if you use DAS cables on the surface, it is probably a good idea to choose engineered fibers, as it could increase quite significantly signal to noise ratio. And also if you're using far offset sources, engineered fibers can improve the signal to noise ratio of your signal. And also we have tested the use of double SOVs, double motors, so we can improve the low frequency response. So I'd like to acknowledge the funding received for both of these projects from the DOE. And thank you for listening, and I can take any questions.
Great, thanks so much, Julia. That was a great talk. Are there any questions We have one. Let's see, I'll go ahead and read it, Casey. Julia, could you give us a rough idea of the cost difference between single mode fiber and engineered fiber?
So I think this depends. I'm not really the best person to ask about the cost. Probably the manufacturers could go and talk about this, but it may vary between 2 times or 3 times. But I can say that we've seen that the signal improvement is of about 15 dBs. So, you know, this can be a difference depending, this can be a significant difference depending on your project.
All right, well, that wraps up the user experiences portion. Everybody gave some really great talks, and now we have a little bit more tools in our bag for the next DAS experiments to come.